Hey everyone, and welcome. So today we're going to tackle a question that sounds like it's straight out of science fiction. How do you find your way around when you're literally in the middle of nowhere, in the vast, empty blackness between stars? I mean, forget your phone's GPS. When you're billions of kilometers from home, you need something, well, something entirely new. And we're going to dive into a really brilliant solution that actually turns the stars themselves into a navigation system. I mean, just to really get a feel for the scale of this problem, think about the Voyager 1 probe. It's out there, right now, cruising through interstellar space. And just figuring out where it is, precisely, is one of the toughest challenges in science today. To put a number on it, Voyager 1 is over 163 astronomical units from us. Now that means it's 163 times farther away than the Earth is from the Sun. At that distance, a radio signal, which, travels at the speed of light, takes more than 22 hours just to get there and another 22 hours to come back. So if you ask for directions, you're waiting almost 2 full days for the reply. So yeah, clearly, trying to rely on our Earth-based systems like the Deep Space Network is just not going to cut it for future autonomous missions. It's too slow, not precise enough. What we really need is for a spacecraft to be able to figure out its own position, on the fly, anywhere in the galaxy. We need a GPS for the cosmos. And to build it, scientists are looking at some of the most incredible objects in the entire universe. And that solution, it lies with these amazing things called pulsars. Okay, so a pulsar is what's left over after a giant star goes supernova. It's this tiny, unbelievably dense core that's spinning ridiculously fast. And as it spins, it shoots out these powerful beams of radiation from its magnetic poles. So from here on Earth, every time that beam sweeps past us, we see this super, regular, predictable pulse. They are, without a doubt, nature's most perfect clocks, just ticking away with mind-boggling accuracy for millions of years. But here's the thing, when it comes to navigation, not all pulsars are created equal. Your normal pulsars are cool, but the real gold standard are millisecond pulsars. These things spin hundreds of times every single second, and they are phenomenally stable. A lot of the time that's because they're in a binary system, orbiting with another star, which helps keep them spinning fast and true. That incredible regularity makes them the perfect beacons for our cosmic GPS. Okay, so it sounds simple enough, right? You just listen for the ticks from a few different pulsars and boom, you triangulate your position. But there's a catch. The signal that we receive here isn't quite as perfect as the one that left the star. See, space isn't perfectly empty. It's filled with this thin soup of gas and dust called the interstellar medium. And this is the really crucial point. For years, the models we've used to test navigation systems have been totally static. They just assume a pulsar signal is perfect and constant. But in the real world, as that signal travels thousands of light years, the interstellar medium messes with it, distorts it, delays it in unpredictable ways. Using a static map is exactly like trying to navigate a city with a map from last year. Sure, the main roads are probably still there, but you have no idea about traffic jams, road construction, or detours. What we need is a living map. And that is precisely what a team of researchers from the Brno University of Technology came up with. Instead of just relying on this fixed, idealized model of a pulsar, they developed a way to create a dynamic, adaptive model. It's a surrogate model that actually learns from real observations and can predict how a pulsar signal is going to change and evolve over time, capturing all of that real-world messiness. Now, to build this model, the team needed some real data. They scanned the skies looking for the best possible candidates, and one just jumped off the page. A pulsar named J0341+5711. It's about 6,000 light years away, and its flux, which is basically its signal strength, wasn't just a little better than the others. It was nearly 100 times brighter than the next best option. That incredibly strong, clear signal made it the absolute perfect test subject for their new idea. The process they developed is actually pretty elegant. First, of course, they capture the real signal with the radio telescope. Second, they clean it up, filter out all the background noise. But the real magic happens in step 3. They use a type of machine learning that's fantastic at finding hidden patterns in messy data. You can almost think of it like teaching a computer to recognize someone's unique handwriting with all its personal quirks and variations. And then finally, the algorithm uses everything it learned to generate a brand new synthetic signal that's basically a perfect digital twin of the real thing. And what's so powerful here is that the model doesn't just average everything out to create some perfect, clean pulse. No, it learns the pulsar's unique heartbeat, including all those subtle, dynamic changes caused by its journey through space. It can then take just a few real observations and create a continuous, totally realistic prediction of the signal for any point in time. So, of course, the million-dollar question is, did it actually work? Was the signal generated by their living map a good match for reality? The team put it to the ultimate test. They compared the pulse profile generated by their model directly against the actual radio observations they started with. And the results were, well, they were definitive. They used a statistical measure called a correlation coefficient, where a score of 1.0 would be a perfect match, and their model consistently scored above 0.9. That is just incredible. It proved that their synthetic signal was a stunningly accurate replica of the real, messy, dynamic signal beaming at us from across the galaxy. So, what's the big takeaway here? Well, the implications are just huge. This new method isn't just some cool academic exercise. It's a total game changer for space exploration. It lets engineers test their navigation hardware against signals that are way more realistic. It paves the way for truly autonomous spacecraft that can find their own way light years from home. And because it can work with data from smaller radio telescopes, it opens up this kind of cutting-edge research to way more scientists around the globe. So, in the end, this innovation isn't just about making better simulations. It's about giving us a far more reliable map to explore the cosmos. It's a key piece of the puzzle in building that GPS for the cosmos we were talking about. And it leaves us with one very exciting final thought. Once we have a map this good, the only question left is, where do we want to go?